Module 4, Investigation 9, Solving Exponential and Logarithmic Functions. Number 1. Solve each of the following equations for x. Find the exact answer and then use your calculator to approximate the answer to the nearest thousandth. Part A. 4 equals 3 raised to x. So there are quite a few ways to solve this problem. One, we could think about the definition of the log. Log base A of x equals k. Let's not use x, let's use something else like b. Log base A of b equals k. What that means is that a to the k equals b. So here we could simply write log base 3 of 4 equals x. There's our exact answer. We could also use the calculator. Some of you guys have calculators that'll do this logarithm. There's also a change of base formula, which you may remember from high school. This is equivalent to log of 4 divided by log of 3. So you could type it in your calculator that way, just the common log with a base 10. This is about 1.26186. You could have also done this. We have 4 equals 3 to the x. If we know that those are equal, we can also say that this will be true. The log of 4 equals the log of 3 to the x. Now that's true because the log is a function. We know if these inputs are equal, then log of 4, the log of 3 to the x, the outputs will be equal also. Now there's a property of logarithms that says we can take this x down front, x times log of 3 equals log of 4. And then we have x multiplied by log of 3, so we can divide by log of 3. And we'll get x. You could have also taken the natural log of both sides so that you got natural log of 4 over natural log of 3. For number 2, 22.4 equals 17.5 divided by 3.4x. We really want to get a form like this, a to the x equals b. So the first thing we can do is divide by 17.5. And in the calculator we can divide. So we have 1.28 equals 3.4x. So here you have a few options. You could take a log of both sides, like we could take the natural log of 1.28, and since these are equal, then natural log of 1.28 must be equal to natural log of 3.4x. We could then bring our x down front. And then you could divide by natural log 3.4 to get x by itself. You could have also taken this expression and just converted it to log form. That's log base 3.4 of 1.28. In either case, you'll get the same answer, something close to 0.202. So in part A, I was really supposed to just go to 3 decimal places, 1.262, but anyways, that's not too important at the moment. So in each of these problems, we could take a log of both sides. It says, why is it mathematically valid to take the natural log of both sides of an equation? In other words, how do you know the two sides of the equation are still equivalent? Let's see. If the inputs are equal and the natural log is a function, meaning for each input there is only one output, then the outputs of equals are equals. The answer key has a slightly different explanation. Basically, like with part A, 4 equals 3 to the x. We know that, let's see, there's some number e, some exponent e that something we raise e to get 4. Now, if 4 equals 3 to the x, then that same exponent, this question mark here, will work. And the exponent that works is the natural log of 4 in the first case. That's just the definition of the exponent. And in the second case, it's the natural log of 3x. Part B, is it mathematically valid to take the natural log of both sides of an equation if one or both sides of the equation has a value less than or equal to 0? So the answer is no. What's the number that we raise e to get 0? Or what's the number that we raise e to get a negative? The answer is there are no numbers. The natural log of 0 doesn't exist. It's undefined. And the natural log of -1 is also undefined. These values 0 and -1 are not part of the domain of the logarithmic function. The domain of the logarithmic function are all the numbers greater than 0. Number 3. In 2009, the enrollment at Mainland High School was 1,650 students. Administrators predict that the enrollment will increase by 2.2% per year. Cool, there's our percent change, 2.2%. Determine when the enrollment at Mainland High School is expected to reach 2,600 students. Well, I think that we can define a function that gives the enrollment in terms of the number of years since 2009. Let's let t be the number of years since 2009, and let's see, capital E be the enrollment at Mainland High, and let's define f to be, let's define our function f to be the enrollment in terms of the input t. So what does such a function look like? F of t equals our initial value 1650 and the growth rate is 1.022. That's just 1 plus the percent change as a decimal, or 100% plus 2.2%, and then make that into a decimal. And then we need our exponent. This is an exponential function, so we need our t. And we want the enrollment when Mainland High School is expected to reach 2,600 students. So the output will be 2,600 students. And we need to find what is the input that makes that happen. So let's get this in exponential form. Let's divide by 1650. 2,600 divided by 1650. $1.57576. This is an approximation. That equals 1.022t. At this point, we could convert this to exponential, or to logarithmic form actually, and then use our calculator. We use the change of base formula, or we could take a natural log of both sides. The natural log of instead of writing that big number, I'm just going to write 2,600 divided by 1650 equals, that's natural log 1.022t. Then we can bring that t down front. And then we can divide by natural log of 1.22, and we'll get t equals the natural log of 2,600 over 1650 divided by the natural log of 1.022, which appears to be about 21 years. Okay, part B. Suppose that Mainland High School requires 5 teachers per 65 students. How many teachers are required if the enrollment is 2,600 students? Let's see, so there are 2,600 students. If we divide that by 65, we can find out how many groups of 65 that we have. Then we need 5 teachers for each of those groups. So 5 times 40 is 200. Part C, define a function f that gives the number of years since 2009 in terms of the number of teachers employed by Mainland High School. Well, we had this function where E was the enrollment, that's the number of students. But instead of number of students, we want this to be number of teachers, which is, let's let I don't know, n be the number of teachers. Then if we take the enrollment, so E divided by 65, the enrollment divided by 65 tells us the total number of groups of 65 students that we have. Then just like above, after we divided by 65, we multiplied by 5. We multiply this by 5, and that'll tell us the number of teachers, N. So notice that if we solve this equation for E, 65 over 5 times N equals E, I just multiply both sides by the reciprocal of 5 over 65. It cancels there, and we get 65 over 5 times N is E. And so, since I want my function to give us N, actually what I want it to give us the number of years in terms of N. So I'm going to replace this E here with 65 times 5 over N, and that's 13N. So 13N equals 1650 1.022t. We know that this relationship will hold. 13 times the number of teachers equals the initial number of students times our growth rate times t. And we really want t by itself. We want a function f that gives the number of years. We want our t to be in terms of f of n. And the work that we've already done up here gives us a clue of that function. Notice that t is equal to natural log of, in this problem it was our output 2600, and here the output is 13n, divided by the initial value, 1650, the initial number of students, and all that is over the natural log of the growth rate. And we have our function. Number 4, recall the alpaca problem from Module 4 Investigation 4, which stated, a farm in Canada had 218 alpacas on January 1st, 2004. After 8 years, the alpaca population decreased to 187. Assume the number of alpacas decays exponentially. They find a function f that expresses the number of alpacas on the farm in terms of the number of years since 2004. So first, let's define some variables. Let t equal the number of years since 2004. Let's let a be the number of alpacas. And let's let our function f of t equal a. So notice that we have a couple values. Let's see, so on January 1st, 2004, in year number 1, we have 218 alpacas. And 8 years later, we have 187. If we take 187 divided by 218, we get about 86%, 0.86. That's the decay factor, the 8-year decay factor. But we want our function f to express the number of alpacas on the farms in terms of the number of years, so 1 year increments. So since we have the 8-year decay factor, we can take the 8th root of that decay factor, or 0.86 to the 1/8, and that will tell us the 1-year decay factor. And that's about 98%. So our function, which gives us the number of alpacas, is the initial value of alpacas, 100 or 218, times our 1 year decay factor, 0.98, and our exponent t, the number of years since 2004. I noticed that the answer key had this function that is equivalent 0.218. I'm sorry, not 0.218, just 218. They used the 8-year decay factor. Then they took the number of years and divided by 8, which is essentially what we did with 0.86 to the 1/8. This is 218.86 to the 1/8 to the t, which is the same thing as our function, 0.98t. Use the function defined in Part A to estimate the number of alpacas on the farm in 2013. Well, in 2013, that is 2013 minus 2004. See, how many years is that? 9. So that's our value of t. And so our function tells us the number of alpacas after 9 years in 2013 would be 218.989. You should get something around 182. I think the book kept more decimals with their growth factors, and they have 183 alpacas. So, yeah, somewhere around there. Part C, determine the year when the number of alpacas was 165. Solve algebraically and then check your answer using a graph or by using your function defined in Part A. So, if we know the number of alpacas is 165, we have our function f of t, which tells us the number of alpacas. And now we're looking for the year, the t. So we know the output is 165, and we'd like to find the value of t that gives us that output. So we can divide both sides by 218. So we have exponential form. Then we could take a natural log of both sides. We could keep the left-hand side the same, but on the right-hand side we can use the property of logarithms where we bring our t down front, and then we have t multiplied by natural log 0.98, so to get t by itself we divide. T equals the natural log of 165 over 218 divided by natural log of 0.98. Okay, I got about 14. So in the year 14, we'll have about 165 alpacas. Let's check that using the function in part A. F of 14 would be 218.98. 14 and that is 164.294. It's a little bit less than 165. That's because we rounded off our growth factor. Probably should have kept more decimal places there. If you're ever dealing with money, you don't want to round off too soon, because then your final answers aren't quite correct. You may lose some money. Anyways, but that's okay. Pretty close. Let's see, number 5. In 1928, 22 koala bears were introduced to Wallaby Island. In 1992, the population of koala bears on the island was about 2,000. Assume the population of koala bears can be modeled by exponential growth. Part A, determine the annual growth factor in this situation. So notice that in 1928, we had 22 koalas, and in 1992, there were 2,000. Now, this is a change of 1992 minus 1928. 64 years. So if we divide 2,000 by 22, let's see, 90.9091, this is our 64-year growth factor. But we would like an annual growth factor, a 1-year growth factor. So we take our 64-year growth factor. And we know if we took the annual growth factor and multiplied it by itself 64 times, it would be 90.9091, so we can take the 64th root. And that is 1.07301. There is our annual growth factor. Solving algebraically, determine in that year the population of koala bears on the island will be 4,500. So first, well, let's see, how could we do this? I think we need an equation. So let's let t be the number of years since 1928 and k the number of koalas on the island, and let f of t equal k. Then f of t is equal to the initial value 22 times our growth rate, 1-year growth rate, 1.07301, and our exponent is t. Now this function output tells us k, the number of koala bears, so we want the population to be 4,500. We want to determine the year when that will happen, so we're using our function to predict. And so we can just solve this equation for t. So we can take 4,500 and divide by 22 to get an exponential form. Now we can take the natural log of both sides. we could have used a common log. Now we bring our t out front on the right hand side. Okay, so now t is multiplied by this natural log. We can divide by that and get t all by itself. Natural log of 4,500 over 22 divided by a natural log of 1.07301, which is somewhere around 75 and a half. So 75 and a half years, then the koalas will reach a population of 4,500. And if we took 75.5 and added it to 1928, we'll see that it's in the year 2003. So that's the year. I think that's all I assigned you guys for homework, but I'm going to go ahead and solve number 6 and 7. Number 6, you deposited $2,500 in a CD to help save for your college tuition. The annual interest rate of the CD is 4.5% compounded continuously. Define a function that gives the value of the CD in terms of the number of years that have elapsed since you opened the CD. So in general, the value, or the continuously compounding formula, is our, let's see, our future value. Let's call it A equals the principal times e to the interest rate and the time in years. So you deposited $2,500, and we're compounding in, let's see, continuously, 0.045 t, and let's see, so yeah, there's our function, 2,500 e 0.045 t, where t is the number of years since you deposited the money, a is the future value of our CD, and p is the present value of the CD, which is fixed, 2,500. How many years will have elapsed before the CD is worth $7,000? So CD is worth $7,000, so we know that's equal to 2,500 e 0.05 t. Let's divide by 2,500. That is 2.8, so 2.8 equals e 0.045 t. Now we can take the natural log of both sides, and since the natural log is the inverse of the exponential function, this right hand side is just 0.045 t. Then we can divide, so our final answer is natural log of 2.8 divided by 0.045. Which is about 22.88. 22.88 years. Number 7, Jasmine has $13,570 to invest in a savings account. Determine the number of years before her money doubles at an annual rate of 4% compounded continuously. So our compounding continuously formula, once again, A equals P ERT. So our 13,570 is our present value, and our rate is 0.04, and t, and that's going to be our function, which will give us the amount in the savings account. And we want to determine the number of years before her money doubles. So the amount is going to double. Really, we can think of it like this: 2 times the amount, 2 times the amount deposited equals the initial amount deposited, ERT. Let's divide both sides by p here. You see 2 equals ERT. Then if we take the natural log of both sides, on the right hand side we just get RT since those are inverses. And so t equals the natural log of 2 divided by the rate, which is 0.04. And that is 17.329 years. Part B, determine the number of years before her money doubles at an annual rate of 7% compounded monthly. So if we're compounding monthly or quarterly or annually, so n is the number of times compounded per year, t is the time in years, r is the rate as a decimal, p is the present value, a is the future value. Let's see, so again we want the money to double, so 2p equals p 1 plus r over n in t. We can divide both sides by p. That cancels out. And we're compounding monthly, so n is 12. The rate is 0.07. 12t. Now we can solve this for t by taking the natural log of both sides, bringing down the 12t. And we should get t is about 9.931 years.